Hello everyone, thank you for joining us today. I appreciate you taking the time to listen in. When I was a kid, I loved to lie out in the backyard late in the evening and look up at the night sky, as I'm sure many of you did. I'd search out all the constellations and as many planets as I could find. But my favorite things to see were the shooting stars. They were like brilliant fireballs passing from another dimension into ours for just a moment and then back out again. If it wasn't a particularly active season, spotting one was lucky because it'd be here 1 minute and then gone forever the next. And if you were looking in the wrong place, you'd miss it. They were always a treat and they were always dazzling. During those nights in my backyard, looking up at shooting stars, I had no idea that one day I'd be an astronaut on a mission aboard the International Space Station looking down at shooting stars. As you probably know, what we call shooting stars are really pieces of asteroids. Rocks in space, large and small, soaring through our solar system. And unfortunately, history has made it abundantly clear that asteroids are not always dazzling. Sometimes they're deadly. Just ask the dinosaurs. Of course, you can't ask the dinosaurs because they're extinct. And the reason they're extinct is because one day in their lifetime, the Earth got slammed by an asteroid. An asteroid about 6 miles across that wiped out nearly all life on the planet. Whether or not the dinosaurs saw it coming, there was nothing they could do about it. Since we live on that same planet as the dinosaurs, the thought of an asteroid nearly wiping out all life on Earth is pretty scary, especially if there's nothing you can do about it. So our response might be, well, that was way back then. We don't get hit by asteroids anymore. So we're safe now, right? Well, about 50,000 years ago, the Earth was hit by another asteroid, this time in what is now Winslow, Arizona. This was the result, the Barringer crater. You can go visit the site today. That asteroid was only about 160 feet across, much smaller than the asteroid that killed the dinosaurs. But the crater itself is about 3,900 feet across, almost 600 feet deep, and has a rim that's almost 150 feet above the plains. You wouldn't want to be out there photographing the nearby landscape when that thing hit. That's another scary thought. We might say, well, that was still way back then. We don't get hit by asteroids anymore today. So we're safe now, right? Well, just over 100 years ago, in 1908, another asteroid hit the Earth, this time in Siberia. It's referred to as the Tunguska event. That asteroid was even smaller than the one in Arizona, about 135 feet in diameter. But the impact of that asteroid laid the trees out flat, as you can see here, in about a 20-mile radius. If that asteroid landed today in a major city like Miami or Paris or London, it would be total destruction. And just 6 years ago, a shockwave rocked a major metropolitan area in Russia known as Chelyabinsk. The shockwave was caused by an asteroid. This one was even smaller than the one in Siberia, only about the size of a room, and it flew 18 miles over the city. Since nearly every car in Russia has a dash cam, you can watch videos of the asteroid on YouTube as it soars through the sky. You can also see the damage it caused. In the few seconds that the asteroid was in our atmosphere, it injured 1,500 people from things like shattering glass and damaged 7,200 buildings in 6 cities. Now, when we hear all that, we may change our response a little and say, well, okay, but look how much smaller the asteroids get over time and less destructive. So we are safe now, right? Well, take a guess. Better yet, let's take a look. When I was a kid looking for shooting stars in the backyard, this is what we were taught about our solar system in school. 1 sun, 9 planets. 9 planets at the time, with respects to poor Pluto. Now, this picture, like the models we saw in school, is not to scale. There is a huge amount of distance between the planets in our solar neighborhood. At their closest points to us, Venus, our nearest neighbor on one side, is about 25 million miles away, and Mars on the other side is more than 33 million miles away. And all the planets stay in their orbits, which fortunately never cross ours. So we may be lonely as a planet besides the moon, but we're also very safe, at least according to this model. Of course, in later school years, we learned about a few other objects. They're not from around here, but they do pass through the neighborhood every now and then, the comets. Although they don't orbit our sun, they do have orbits that also, fortunately, don't cross ours. So on occasion, we get to see these brilliant cosmic visitors, but our planet is still very lonely and very safe. at least according to this model. But modern science now gives us a much more detailed model. We can see through our current telescopes that there are still other objects out there, locals in our solar neighborhood, also orbiting the sun with us, the asteroids. In fact, when we account for all the asteroids we can see, the model of our solar system actually looks like this. So back to our earlier question, we're safe now, right? Well, as we've seen, our asteroid neighbors don't always keep to themselves. Sometimes they wander over into our yard and mess things up pretty badly. The truth is, we still get hit by asteroids every day. So as you can see, we are not living in a virtually empty solar system. According to this model, we're living in a cosmic shooting gallery. Now, the good news is that most asteroids that come in contact with the Earth are fairly small and usually explode harmlessly in our protective upper atmosphere. Although they're very dense, asteroids are also crumbly, and traveling at 20,000 to 50,000 miles per hour means that crashing into our air is usually enough to shatter them into the tiny glowing pieces that we call shooting stars. The Moon doesn't have a protective atmosphere like ours. That's why it looks like this. Giant potholes from asteroid impacts. And finally, since the Earth is mostly water, the few pieces of asteroid that actually survive the crash through our atmosphere tend to land in an ocean, and we never even hear about them. So that's the small asteroids. Here's the good news about big asteroids. The first time you look down from an airplane at a major interchange of several multi-lane freeways packed with cars all traveling at high speeds, you think, wow, that is a disaster in the making. But the reality is there are remarkably few collisions on our freeways. The cars follow a variety of set paths. Same thing with asteroids. Since they have fixed orbits, there are virtually no collisions between big asteroids and the Earth. But virtually no collisions isn't the same as absolutely no collisions. And just as history shows us that big asteroids have hit us in the past, and YouTube videos show us that a big asteroid hit us recently, modern science confirms that other big asteroids are on a collision course to hit us in the future. But here's the good news. We can stop them. The science that helps us predict collisions also enables us to prevent them. In fact, even though an asteroid collision is the one natural disaster that doesn't originate on the Earth, it's also the one natural disaster that we can eliminate. I'll tell you how we do it. But first, let me tell you real quickly how we don't do it. Unlike in the movies, we can't destroy asteroids in space, even if we hire Bruce Willis. They're just too big and dense for even a nuclear weapon to deal with reliably. So what can we do with asteroids that are on a path to hit us? In principle, it's actually pretty simple. All we have to do is delay them. Here's how it works. Asteroids circle the sun in fixed orbits. The Earth, of course, also circles the sun in its own fixed orbit. That means three things. Number one, we're a moving target. Number two, the only theoretical way an asteroid can hit us is if our orbits cross at some fixed point. And number three, the only actual way an asteroid can hit us is if we're both at that fixed point at the same time. And by the same time, I mean within a few minutes. The Earth is a fairly big target, and it takes a while for its entire mass to move through any given point. If the asteroid hits us anywhere at that fixed point, or at any angle, or even flies by close enough, it'll do some damage, as we saw in Chelyabinsk. But that has to happen literally within a few minutes, or no harm done. In other words, there's a very small window of opportunity for a collision. What that means is that if on collision day, that asteroid shows up just a little bit late, we will have already passed safely through that fixed point, and there will be no collision, not even a shock wave. And that is the key to our solution. We simply make the asteroid late. And we do that by slowing it down. So, how do you slow down an asteroid? Well, there are two methods. In the first method, you use a spacecraft known as a gravity tractor, which a colleague of mine and I invented. You just hover it near the asteroid for several months, and the mutual attraction of gravity between them, though it's very, very small, slows down the asteroid. The second option is a bit more fun. We just slam a rocket into the asteroid and blow the rocket up. The impact of the explosion slows down the asteroid and gets a cheer from the kid in all of us. Now, in both cases, the reduction in the asteroid's speed, the amount that the asteroid slows down, is tiny. We're talking about a few millimeters per second, about the speed that an ant can crawl. But here's the thing. You only need a tiny reduction in speed if you have a huge amount of time. It's like emptying a bucket full of water by poking a tiny hole in the bottom. After a minute or so, you won't notice a difference in the water level. Even an hour later, there may be no visible change. But after a day or a week, you're going to come back to an empty bucket. Time is our key ally. With enough time, the smallest change can make a huge difference. That same principle applies to stopping asteroids. If you slow down the asteroid even a tiny bit, but you do it early enough in advance, like 10 or 20 years in advance, then when collision day arrives, that asteroid won't. It'll get there eventually, but it'll get there too late. This process is called deflecting an asteroid. It's incredibly detailed, but it operates on the basic physics we just looked at. And we know it works because we've already done it. In 2005, we ran a mission called Deep Impact, where we flew a rocket into a comet and slowed down the comet. So, to stop an asteroid from hitting the Earth, we just locate it, calculate its orbit, launch a rocket rendezvous 10 or 20 years in advance, and no collision day. Problem solved. So then, the answer to our original question, are we safe now, is yes. At least according to this model. There's just one more problem. This model shows the asteroids that we can see with our current telescopes. It doesn't include the asteroids that we can't see. We know there are a few of those out there. In fact, if the model of the asteroids we can see looks like this, then the model of the asteroids we can't see looks something like this. Yeah, the yellow dots are the asteroids. And since we've determined that a few asteroids are on a path to hit us from the smaller group that we can see, you can bet there are even more on a path to hit us from the bigger group that we can't see. And what you can't see, you can't prevent. So why can't we see those asteroids? Basically, our current telescopes are limited in 3 areas. Those areas are visibility, range, and time. Let me explain those real quick. Regarding visibility, asteroids are dark like charcoal, so they don't reflect sunlight. Locating the asteroids that are close by is one thing, but trying to spot a relatively small, dark, fast-moving object from millions of miles away against the dark background of space is nearly impossible. On the other hand, trying to see them while looking into the blazing sun is just as difficult. You're just not going to find them. The second limitation is range. From the vantage point of our home planet, our range of observation is very small. It's basically like this small white half circle on the edge of the Earth's orbit. An asteroid has to come into this range in its own orbit for us to see it. Compared to the size of the area we need to look at, this area around the Earth, that range is nowhere near sufficient. And the third limitation of our current telescopes, time, is really a function of the first two. As one of my colleagues put it, the trick to stopping asteroids is find them early, and find them early. As I said, deflecting an asteroid is easy when you've got a 10 or 20 year head start. But if you don't have the visibility or the range to see them early, you won't have the time to slow them sufficiently. And what you can't see in time, you can't prevent. Fortunately, there's more good news. Even though we can't see those asteroids, there's one thing that can. We call it Sentinel. Sentinel is a satellite telescope currently in development. It's about the size of a FedEx truck. When it's completed, it will be like no other telescope in the world, or off the world. Let me tell you about Sentinel in terms of how it overcomes the 3 limitations that hinder our current telescopes. Here they are again. First, visibility. As I said, asteroids don't reflect light from the sun, but they do absorb heat from the sun. And because they absorb heat, they give off infrared light. And against the cold background of space, that infrared light shows up very well. It's quite visible to an infrared telescope, and Sentinel will be equipped with an infrared telescope. Now, a quick note about that. You might ask, why don't we just set up infrared telescopes on the Earth? Here's why. Because our atmosphere, which so effectively absorbs the impact of small incoming asteroids, also effectively absorbs infrared light. so that light from the asteroids never gets to our telescopes on Earth. You have to put the telescope in space. That brings us to the second limitation of our current telescopes and how Sentinel overcomes it. In addition to being unhindered by the Earth's infrared light-absorbing atmosphere, Sentinel is also unhindered by the Earth's limited range. Obviously, because it's a satellite, it won't be on the Earth like other telescopes. It also won't orbit the Earth or be anywhere near the Earth like the Hubble telescope, which orbits the Earth at about 350 miles from the surface. Sentinel will be out toward Venus, so it'll be about 25 million miles away from us at its closest point. Also, rather than orbit the Earth, it will orbit the Sun with its back to the Sun, facing outward toward the Earth and toward the asteroids. With that kind of range, literally no telescope on Earth can match it. Here's a comparison. This is the range again for our current telescopes, the small white half circle, and here's the range for Sentinel, this giant gray half circle. That's about 100 times the range that we have on Earth right now, and that range is more than sufficient to find the asteroids we need to find. The third and final limitation is time. As I said, it's a function of the first two limitations. If you don't have the visibility and the range you need, you won't have the time you need. But if you have plenty of visibility and plenty of range, you'll have plenty of time. Sentinel, with its infrared vision and massive range, will give us all the time we need. And with the data that Sentinel will transmit back to us, we'll be able to calculate well in advance which asteroids are a threat. And the solution, once again, is basic physics. Because what you can see in time, you can prevent. So, back to our original question once more. Are we safe now? Well, has the solar system run out of asteroids that are on a collision course with Earth? The answer is no. But can we find those asteroids in time and prevent that fate? With Sentinel, the answer is yes. When I was a kid, I loved to look for shooting stars. Today, I have kids of my own. We love to lie out in the backyard late in the evening and look for shooting stars together. In the time of the dinosaurs, when one of those shooting stars turned out to be deadly, they had no ability to stop it. But today, we have that ability. We can ensure that our children and our children's children will continue to see shooting stars as nothing more than dazzling. Thanks very much.